um, said that if we have losses, if we have losses, then we will. All right. So if we have losses and we want to know the uh, 95% risk, then we will take this value such that this area is 95%. Um, and if we take returns, or if we take gains, for let's go back to gains. Just 1 minute, let me erase this bar. Say, if we have gains, then we will look at, there may be a zero value somewhere here, which would be, I mean, then this would be the kind of loss that we are looking at. So G star will be a negative value, and we will select that value such that this area is 95%. Okay, or we can look at returns as our, and again similarly, this this may be a zero value, and we can say this R star is the worst return we can have, such that this entire area is 95%. And we also talked about, so this R star or this G would be kind of a, this R star, this G would be kind of, absolute values at risk. Whereas if we want, there is something called a relative value at risk, then we would compare this with the average, which is typically the expected value. Okay, so the absolute value at risk would be this much, whereas the relative value at risk would be this much. All right, so this is what we have done. Then we said that how do we get this? Say the gain. So say the gain. No, no, no. So it's not writing. Okay. So okay. So how do we get this G star or R star? We said we will download some data, and so we can get values of losses or historically. So let's say 1, 2, 3 till t days of data. It could be say the last 20 years of daily data, and compute the gains, maybe daily gains, which would be delta in prices, say, or the returns, and this is better basically, which would be delta p by, rather we would say it is pt minus pt minus 1 divided by pt minus 1. So this would be a return figure. Either way, we could, get last t days of data, get the gains or the returns. Now we said there could be two ways to find the worst gain or the worst return, by sorting these gains or sorting these returns and selecting that gain or that return such that 95% of the data lie above, and uh, and only 5% of the data lie below. So this is the, we call this the non-parametric or empirical value at risk. Why it's called a non-parametric value at risk? Because we are not assuming any distribution, that the data follows any distribution. We are just assuming reading out this worst gain or the worst return from the data per se. The other thing that we said, what we can do is fit a distribution, assume distribution. See, we should always remember that nobody in the world has told us which distribution gains or returns follow. In fact, it may not follow any known distribution. It can be just a God knows distribution if there were such a distribution. But we will assume. So we can. So the moment we look for parametric where basically we are assuming a distribution, and the moment we assume a distribution we have to, so if we assume normal distribution will have a mu and sigma squared. These are the two parameters of the normal distribution. Where do we get these mu and sigma squared from? Again, looking at this entire data only. So from this entire data we get the mu, estimate of the mu and estimate of the sigma squared, because again the population mean and the population variance nobody has told us. So these are sampling estimates of, so because they are sampling estimates we can also write them as x bar and s square, because these are not the population data. um, the moment we come to x bar and s square, you should remember that this very largely depend on the sample that you have chosen. So we might have chosen, one of you might have chosen the past 5 years of data, which would include the pandemic. But somebody might have taken last 20 years of data, which would include other bad times, the 2008 meltdown and all that. So depending on which set of data, so this is very much dependent on this kind of data that you have taken. But still, looking you estimate these parameters looking at the entire data set, either the gains or the returns, whatever, but you estimate. So these are called parametric words, because when you get these estimates, after that, from the normal distribution tables, you can read out what is the 5% cutoff. You don't need to go with the values. Now, so which bar do you think will be a better measure? Should you fit a distribution and get a VAR? Is that a better measure? Or whether you should look just at the data and find the non-parametric VAR? Which VAR do you think should be a better measure? Any volunteers to answer this question?
Ma'am, maybe if the data has quite some number of outliers, it would be better to use a non-parametric var.
Okay, because it will be why was outliers?
Ma'am, because if there are quite some number of outliers, if we assume any kind of distribution for it, it mean like if there are regular outliers or like regular outlandish trends in the data, so putting a distribution on it might not give us the best results since like we assume a
So
certain
that's,
trend.
yeah, I agree. So that's a good answer. Let me counter that, and it's important that we keep countering each other. Otherwise, we won't be able to have it. So, can you please identify yourself? I can't see your names while I'm sharing the screen. So, can you please identify yourself? What happened? What's your name? Who just spoke? Come on, don't be worried. Who just spoke? Okay,
Sorry, ma'am, my mic was not working. It was me, Arnesh.
sorry,
Arnesh, it was me, Arnesh.
Anish. Anish. Okay, okay, Anish. That's a good justification. Let me give you you know. So everybody, anybody, any else, and any other point that you would like to speak of? Anybody else has a
Yes, ma'am. This is Karthik here.
Karthik, tell me.
Ma'am, actually, we can test for normality. We can conduct some tests for normality, and if they are being satisfied, then maybe we can say that it is fair to assume that it is a normal distribution or whatever kind of distribution we want to test.
Okay, and then
And then we can say that parametric value at risk is a better measure since our assumption is being validated by the test that we are conducting.
yeah, I mean tests would you will all you know there are always type 1, type 2 errors. So yeah, one thing that to but Arnesh had a very good point that if I have say minus 20 crores of loss in 1 year and then minus 5, minus 4, minus 1, minus 0.5 and all that, he kind of said that my VAR will be able to um, take into account this outlier. Is that what you said, Arnish? Okay. I'm hoping your mic is not working very well. So suppose somehow I have the problem with VAR is it actually does not take into account what values of the past data were there. It just reads out what is a cutoff value. So, you might get a VAR as 0.5. On the other hand, if I could estimate a mean, don't you think this outlier would pull the mean back? So if I were to put a distribution, this outlier, if I have it in my data, this outlier would actually pull my mean back. And so my normal distribution also, and so I might be able to get a good, you know, I think what you're trying to say is being kind of we should be as negative as possible so that or so that we can capture the worst things that are there. So whenever we calculate mean, such outliers would actually be somehow captured through the mean, unless and until you probably have say 500 data points out of which this is just one value, and so that one value might get um, uh, you know uh, kind of removed when we take a var, but still this would slightly pull the mean back, if not maybe not a lot, but it might pull the mean back. The basic argument in favor of this parametric var is this, that the non-parametric var does not take into account the entire data set. It only checks because you have sorted the data and you have taken so suppose you had 500 data points here. That is your t was equal to 500. So if I want the 95% value at risk, you would pull out the 25th value. Sorry, 25th value, right? And then just find what is the var. Um, so it does not take into account the data points at all. In fact, it just takes the 25th value, and whether this was minus 20, whether this is minus 5, it does not care. Whereas the parametric var takes into account the entire data set. Now remember that these are very see on top. This top of the iceberg is like the tip of the iceberg. You just haven't seen the worst, maybe. So the worst may be actually still yet to come, or maybe you have not even selected the correct iceberg. So this 25th value from the top actually does not take into account the entire data set, whereas the distribution will take into account all the information that is there in the data set, the variance in the data set, the all the values in the data set and all that. So in fact some people also try to find the distribution with the skewness and kurtosis and all that. We won't get into all the details, but the mean and sigma square actually take into account the entire data set, and that's why it's a more robust, it gives a more robust data described value at risk rather than the non-parametric var. Okay, so that's my argument against your Arnesh's argument. And if you have any further points, please do feel free to speak out. Okay, so that was the parametric var, and we also had done something like a time aggregation. So we said, okay, when we look at parametric var, we will fit a normal distribution. There are other distributions you can fit, the student's t distribution, Weibull distribution, or generalized parameter distributions and all that. But then we said normal is the best. One of the reason normal is the best is because we can do what is called time aggregation. Okay, time aggregation. So what did we say? That if I have daily data, yeah, I have daily data 1, 2, 3, 10. Say I have got last 220 years of daily data. Assuming 250 days of trading, 20 years of daily data would be around 5,000 data points. Um, this is daily, and this is say annual. So if I go for annual, then I will have only 20 data points. Now, if I use a normal distribution we know, if say if R1 follows a normal distribution with mu and sigma, say mu1 and sigma1 square, and R2 follows a normal distribution with mu2 and sigma2 square, then we know that normal distribution has this very nice property that R1 plus R2 will follow a normal distribution with mean mu1 and plus mu2 and variance of sigma 1 square plus sigma 2 square if they are uncorrelated. Even if they are correlated, it will be covariance of R1 and R2. So I don't have space. Just understand that this is. What are you doing? I don't want to delete that thing. Just leave it. So let's try. Let me try to retrieve this. Okay. So it will have a. If R1 plus R2 will follow a normal distribution with mean mu1 and plus mu2 and variance of sigma 1 square plus sigma 2 square plus twice covariance between R1 and R2. Okay, so this is a very nice property that normal distribution has, which other distributions do not have. I mean, a student's distribution, you cannot write it this way. So what happens is, if I want to have a summation of Ri over a year, because I have got daily data, from there I want to go to annual values, I can just sum it over 250 days. So if I basically say all my Ri's follow the same distribution, Ri's follow the same distribution mu and sigma square, which I've got from the entire 5,000 data points estimate, then I can say summation of Ri follows a normal distribution with 5,000 mu, right, and 5,000 sigma square. So for me, this time aggregation is very easy. And so going from a daily value to an annual value for me is very easy. Whereas, so sorry, I made a mistake here. If I want to go from a daily var to daily distribution to annual distribution, if I assume 250 days of data, then this will be 250 sigma square. And therefore, the standard deviation, remember, will be sigma root over 2 4, that is root t, sigma root t. So that is, if I assume, so from a daily to an annual, it's very easy for me to do. I don't have to take annual data and then recompute the mean and standard deviation for an annual kind of a time period. Whereas if I do this for a student's distribution, the problem will be I do not have such a nice expression for students t distribution. Okay, and then what I have to do is, if I have obtained the estimates of a student's distribution from daily data, I cannot directly go. So I have to take annual data and fit another student's distribution on it to get the mean, variance, and the degrees of freedom. The problem there is you have only 20 data points, and maximum likelihood estimation is better as you have more and more data points. So in this, the number of data points actually reduces. Whereas when we are with normal distribution, we don't lose our the information that we had earlier. So that is the benefit of using a normal distribution, because it helps us to do a time aggregation. Now, in the last class, when we were doing this time aggregation, we said we ignored this covariance part because we said we are assuming that prices follow a random walk, and hence there is no the returns over each day are uncorrelated. That is, R1 and R2 are uncorrelated to each other, but they're identically distributed. They're independent of each other, but they're identically distributed. That is, R1 follows normal with mu and sigma square, and R2 also follows normal with the same mu and sigma square. I think this is going bad, so let me not repeat this. But what if they are not independent? Sometimes we have seen returns may be correlated. If returns are correlated, then what we write is RT is equal to rho into RT minus 1 plus epsilon t. The assumption is the this error term and the returns are uncorrelated. That is, there is no correlation, and or rather, the covariance between error terms and the return terms is zero. Now, if I write it this way, then what have I written actually? I am saying R2 is equal to rho into R1 plus epsilon 2. R3 is equal to rho into R2 plus epsilon 3. But now I can replace this R2 with the previous expression. So I can write rho in rho square R1 plus rho epsilon 2 plus epsilon 3. Similarly, R4 I can represent as rho cube R1 plus some functions of epsilon i's, 1, 2, 3, 4, whatever. So, so now if I want to find out variance of say R1 plus R2 plus R3 plus R4, this will be definitely variance of R1 plus variance of R2 plus variance of R3 plus variance of R4 plus 2 into covariance between R1 and R2 plus 2 into covariance between R1 and R3 plus 2 into covariance between R1 and R4 plus 2 into covariance between R2 and R3 plus 2 into covariance between R2 and R4 plus 2 into covariance between R3 and R4. Right? So we will have all these covariances, because now we are saying they are correlated to each other, they are not independent, but we still continue with that identically distributed assumption. Now, what can I write? 2 into covariance R1, R2 will be equal to, so we want covariance between R1 and R2. Covariance between R1 and R2 would be basically covariance between rho R1 plus epsilon 2 and R1. I'm not writing all that, hoping you will understand. Okay, so let me write covariance between R2 and R1 is nothing but covariance between rho R1 um, plus epsilon 2 and R1, which is equal to covariance between rho we are assuming a constant of this equation. This is a constant, and so this is a constant, so it will come out. So we will have rho into covariance between R1 and R1, which is nothing but covariance of R1 and R1 would be sigma square plus covariance between epsilon 2 and R1, but we have assumed they are uncorrelated. So we will not have this. So covariance between R2 and R1 can be replaced as rho sigma square. So this one can be replaced as rho sigma. R1 and R4 can also be replaced with, otherwise we should also put 2 rho sigma square. And R2 and R3 should also be same as 5 rho square. Now what can we say about R2 and R4? R2 and R4 will be something like this. R2 will come here in in this equation. R3 with R1 will be similar as R4 with R2. So covariance between R2 and R4 would be rho square. The rest of the terms are uncorrelated. So covariance between R1 and R3 can be replaced by twice rho square sigma square. R1 R can also be replaced as twice rho square sigma square. Finally, R1 and R4, if you notice from here, covariance between R1 and R4 can be replaced by twice rho cube sigma square. Now, each of these variants of R squares are sigma squares, so 4 of them can be replaced by 4 rho, sigma square. What have I done? What have I done? No, 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 no. How do I get out? I don't know what I did. How do I get out? Okay, okay. So where is this? So, scrolling. Right. So for sigma square, this will be. So now if we can take common, you will notice that this will be equal to, if I take sigma square out, then this is 4 plus 2 into how many sigma square I have taken out? 2 into how many rows? 1, 2, 3. So 2 into 3 rows plus how many row squares? 2 row squares plus 2 into 2 row squares plus how many row cubes? Just 1. 2 into 1 row cube. So I think So I hope you can read this. Which means if I take summation over R4, 4 returns, then I can say the sigma square is equal to 4 plus 2 into 3 row plus 2 into 2 row square plus 2 into 1 row cube. So if I have to kind of generalize this, if I have variance of uh, summation I equal to 1 to t, then this should be equal to sigma square t plus 2 into t minus 1 into row plus 2 into t minus 2 into row square plus 2 into actually t minus 1. So t minus 1 into row to the power of into row to the power of t minus 1. So if if we had assumed there is no correlation, that is these rows are zero, you see we have sigma square into capital T, which is what we had earlier. This is what we had told earlier, that we just have to T into sigma square. But if they have correlations, then we will be underestimating the variance. The variance will be much higher, and this is how uh, the variance will be calculated. But we can still calculate the variance like this and put it in a normal distribution. So summation of Ri will follow T into mu plus sigma square into not T but a lot more other variables. Now this row need not be always positive. There can be mean reversion and all that. If the row is negative, then we will have negative, positive, negative, positive. This may actually even go down. So the variance may, if we disregard the core any covariance in the or if we disregard the dependence between returns, we may and write sigma square like this, then we may sometimes underestimate or overestimate the true sigma square. Whereas if we can find out what is the dependence between this one period dependence, then we can correct it for uh, that much that error. In fact, however, the moment you take row to the typically this row is less than 1. So row to the power of t minus 1 and all need not be calculated. Maximum you can go is till row to the power of 3. Typically row would be zero point 0.4, zero point 0.5 or whatever. So if row is relatively large, say 0.5 or even zero point 0.9. See 0.9 to the power of 3 is very very small. I think what 0.007 I guess. So you can ignore all that. But at least you can go till third or third power or whatever, and then leave the rest. But still, this time aggregation becomes much easier when you assume a normal distribution. Okay, so this time aggregation is possible only when we are assuming a normal distribution, but with others it is not. So this much. Any question till now? I'm talking alone. I would like to have some questions.
Hello, ma'am.
Yeah, please.
Ma'am, these RIs, are they arithmetic returns or logarithmic returns?
Once I finish this chapter, I'll give you this assignment to check out how it matters. You will see that there is so much of measurement errors, and then there are different samples will give you different R stars. Everything will be so different that that is a very minor question. So you will find very small differences in the RIs, whether you do them with arithmetic returns or with logarithmic returns. But that is something that you should, do it on your own and realize that so much of precision is not really necessary.
Also, ma'am, why did you assume RT is equal to rho times RT minus 1 plus epsilon T? Does it have any physical significance?
No. So I don't know whether you have done stationarity or not. Have you done stationarity of time series yet?
We have, but I don't remember it very well right now.
Don't worry, don't worry, don't worry. So sometimes we will say that these returns, the theoretical thing is that returns prices follow a random walk, and so returns are uncorrelated with each other over two consecutive periods. So if you are taking daily data, so returns will be uncorrelated across 2 days, two consecutive days. However, sometimes real data may not conform to that. You may find that today's returns is dependent on past returns. So this is an AR model, an auto regressive model. So what is it? So remember it like this. You know regression. Regression we typically write as y is equal to mx plus c. But if we were to write y is, so we will say y is regressed on x. But if y were to be regressed on itself, just like we say autobiography. Autobiography is writing my own biography. Similarly, autoregressive models in time series are when this you regress a variable on itself with a lag. So you may find that this row is significant, and that which means today's returns depend on yesterday's returns. You may also, so those are basically autoregressive models that you may need to fit. To a little later, you may fit, AR models, MA models, ARMA models, ARIMA models, GARCH models. All of them will make some assumption about this return, about this relationship. Today's returns may have relationship with past returns or past errors also. So depending on that, you may build models when you do time series estimation. So data might tell you that there is such a relationship.
Okay, ma'am.
Is this
Yes, yes.
okay? So if we get such a relationship from the data, then we have to kind of you know revise this formula. That's what the point is, that it may not be t mu and t sigma square, it may be a little bit more than t. If rho is positive, if rho is negative, then it can be even less than t. This multiplier can be different. So, but then you can still apply the normal distribution. Yeah, any other question? Okay. So, it's better to introduce yourself, because if it is for a physical class, I would have seen you, and within, few days, I would have known your faces with your names. Now, though, I have to probably recognize your voices, but at least tell me your names when you ask a question. Okay. So, let's go to one more topic, which is called the conditional value at risk. I don't know, many of you might have already heard this. So this is what is conditional value at risk? One of the problems with value at risk, as we were telling just a little while ago, if I have t days of data, which can be 5,000 data points or whatever, value at risk only asks me to take a cutoff. So if this were the 95% value at risk, I would only take the, sorry, the 25th value, some value, to get so this is, say, returns. And I'm looking for the R star. The worst R star sits such that 95% of the data lie here and only 5% of the data lie here. However, we completely ignore what are the specific values. As I was giving examples, this could be minus 20, then this could be minus 2, minus 1, minus 0.5, minus 0.1, minus 0.1, and then minus 0.01 and so on and so forth. Then after slowly it will become positive also, 0.03 and all that. But so our R star becomes maybe minus 0.03. Yeah, 0.03. And we say that our worst loss is this. The problem with the value at risk is it completely ignored this minus 20, which is a which can have which if it has happened once might happen again also. What conditional value at risks? So VAR basically asks how bad can things get? This is what VAR asks. Conditional value at risk. So, and then how bad can things act? Again, you are saying with 95% confidence level. Okay, with 95% confidence level. Conditional value at risk, what it asks it, if things get bad, what is the expected loss? So then it says if things get bad, what is expected loss? Now what happens is we ask this question, given that returns are less than R star, what is the expected return? Now we will take an average of these values. Correct? That is mathematically we are asking what is the expected value of R given that R is less than R star. That is my uh, let me call it R star. So if there is a very big outlier, my R star star will be pretty high. I mean, you'll see these my VAR would have been minus 0.03% multiplied by W and all that, which we have done earlier, assuming normal distribution or whatever. But the average of these five values at least is how much? When it becomes, what will be the value, average? It will be very, very high, no? 22, 23, 23.6 divided by 5 would have been minus 4.6%, isn't it? Something like that, right? So then my value at risk would have been minus 4.6% rather than 0.03%. And then we would have multiplied the portfolio size and all that, which we have done earlier. That is W0 into R star and into all that. If we are looking at pure relative value at risk or whatever, we have done all that. So I don't want to get into it. So this is the conditional value at risk. Conditional value at risk therefore tells what is the expected loss or expected returns when losses are less than the worst loss that you have assumed, or losses are less than the returns are less than the worst return that you have assumed. So that is the strength of the conditional value at risk. Conditional value at risk does not ignore the values that happened that are above this cutoff point. So condition. So the I could have a okay. Let me just try this out. I can have a distribution like this, or I can have a distribution like, so let me make it very fat tailed. Something like this. The value at risk for both of them, if I were to take this, the value at risk, I mean, might have been same. Okay, so both of them probably have the same area, so the value at risk could have been the same for both. But the conditional value at risk, because you have much higher probabilities of bigger losses, the conditional value at risk might be here, whereas with this, the sorry, With this, it might be here. Sorry. With this, it might be here. So the conditional value at risk takes into account these outliers, which the value at risk doesn't do. The value at risk will also give this, might give. So depending on the distributions, you can create such distributions where the bad is very bad, but value at risk just thinks of a cutoff. It does not look at how bad can things get. It just looks at this cutoff. It doesn't look care about the values to the left of the distribution. Rather, it does not take care about the shape of the distribution to the left of this cutoff. Conditional value at risk exactly takes care because it then takes the expected returns, that is the mean value, once you have this once you have breached the loss. So this is what conditional value at risk asks. If things get bad, what is the worst, how bad can things get? So that is conditional value at risk, and conditional value at risk actually has a lot of good properties. So I will continue all this next class, but at least let me give you some properties of the a very good loss measure. So the problems based on that, properties of a good loss measure. So there was this guy Arzner who gave these properties. Put it up on Teams. If you want, you can have a look at this paper, but it's not very important that you really read this paper. It's slightly mathematical, but so what are the properties of a good loss measure? Up till now, what all loss measures have we seen? The loss measure can be, standard deviation can be a loss measure, that is sigma. Loss measure we have learned can be value at risk. Loss measure we have learned is a conditional value at risk. What is a good loss measure? Um, One of the properties of a good loss measure is monotonicity. So monotonicity says if you have a portfolio which at all points of time produces a result worse than another portfolio. So I have a portfolio P, I have a portfolio Q. On any day, portfolio P is has a. I mean, think of it. Don't think of it stochastically, because stochastically P can have a good return on one day and Q can have a bad return on another day. Although the Q's distribution may be different. See, I'm not talking about distribution right now. You don't think that. Let me draw this a little different. So I'm not talking about. Um, so I'm not saying use distribution of say losses or returns or whatever is like this, whereas P's distribution is like this. This I'm not saying, because then you can pull out one value of P on a day which is better than the value of Q on the same day. Okay, so this is not what I'm talking. I'm talking about a portfolio which has a worse outcome on every day than Q's outcome. The P outcome of P is worse than Q on every day. Then whatever risk measure you take, whatever risk measure you take for P should be uh, worse, sorry, greater than the risk measure of. So if you are looking at standard deviation, then standard deviation of P should be greater than standard deviation of Q. Or var of P should be greater than var of Q. Now standard deviation may not really work, because in that case, the risk measure of P is not greater than the risk measure of Q. the standard deviation may actually fail this test. VAR and CVAR will never fail this test of monotonicity. So if VAR is the risk measure for portfolio P, VAR risk measure will always be greater because you will always get a bigger high value than because as you can see the data points that you will get will always P's data points will always be worse than Q's data points. Okay. So then VAR will take care of monotonicity, but standard deviation may not because the standard deviation may be same or even greater. I mean lesser for P and more for Q. So this is one monotonicity property. Then we have another property called translation invariant. So translation invariant says if you have an amount of cash that you add to your portfolio holdings, your risk should reduce by the amount K. That if an amount, so whatever risk measure you take for P, uh, this should be equal to the risk measure of P plus some cash. The moment you have this, you must be able to, I mean, because you have taken cash here, the assumption is that your total holding is same. So the risk from this should be reduced. This should be equal to plus K. K is the amount of cash that you're holding. So this is translation invariant. That is, if you add some cash to your portfolio, then the risk also reduces by that amount. This is followed by again VAR as well as CVAR. The third thing that we have is homogeneity. Homogeneity is when you change. So if you have a portfolio P and you have a portfolio K into P, then this portfolio, this portfolio should be K times uh, risky than this portfolio. Again, if whether you assume this is followed by even standard deviation. So standard deviation you know is okay. No, it's again not followed by standard deviation. So when you add k times, then this also should get in the risk measure should also get increased by k. The fourth measure is that of sub additivity, and here var fails whereas cvar does not fail. So sorry, sub additivity. Additivity. So here we say that if uh, the risk measure for two portfolios P and Q should be equal to the risk measure for P, the risk measure for Q. Sorry, this. Sorry. Erase. Okay. So the risk measure for P and Q should be less than the summation of the individual risks of P and Q. Okay, this is basically the diversification effect. That is, there will be some risk that will be negated by each of them, so that the risk of holding a portfolio will be lesser than holding these assets individually. Okay, so that is a property of sub-additivity. Now var does not really follow this all the time, whereas conditional value at risk follows this sub-additivity property all the time. We will do some problems to establish or rather demonstrate this tomorrow. But these are the few properties that a risk measure, good risk. I made a mistake. Good risk measure. Good risk measure. So, properties of a good risk measure given by Artsner in 1999 were this monotonicity, translation invariance, homogeneity, and subadditivity. We will show some problems tomorrow, which will show other properties are followed by both var and cvar, but only the subadditivity property is not followed by var, it is followed by cvar, and that is why cvar is supposed to be the most robust measure of risk that can be there. However, having said that, we still will say that we will continue with var. I mean, the real life continues with var most of the time, because again var is easier to use and easier to manipulate and do work with, rather than conditional value at risk. So we'll stop here. If anybody has any question, you can ask. Otherwise, tomorrow we will meet and you can ask more questions as we have classes.
Hello.
Yes, please.
Yes, ma'am, I had a doubt that in real life the stock data doesn't follow the normal distribution. So, how does this VAR give us a good estimate of the risk? Because we are assuming normal distribution all the time.
Yeah, that's fine. You know, we are assuming normal distribution. The idea is, um, I think let's do some problems and data analysis.
Ma'am, your voice is not clear.
Can you hear?
Ma'am, it's breaking.
Can you hear me?
Hello.
Maybe my internet connection is not that good. Can you hear me now?
Yes, ma'am.
So, right, it's not there. You know, first of all, I don't have the true what is there in reality. We don't know. Everything we do, whether we take an empirical data, whether we take student state distribution, which has fatter tails, and we will claim that they are better, they do, model the returns better than a normal distribution. But the a benefit you will get is probably a few hundred rupees out of a portfolio size of say a few lakhs. All right, if you are, if you try to do it exactly correctly, we'll try to do that with data. I hope to start some data analysis tomorrow, because
Okay.
a lot of these will get cleared then. But then, yes, you're right. Theory is that may not follow the real life a lot. However, if you follow theory, it helps you to do certain things, and also whatever you do is a theory only. Even if you do students T, it will be theory only. It won't be a God-given distribution. You don't know what is the true distribution. Empirical distribution is even worse. So, yeah, so in a way you're right, but because it helps us to do work mathematically with a normal distribution, we take this. We give up a little bit of accuracy, but we have to always think, is that accuracy really too bad to give up? Or is there so much of noise in the data that this much of inaccuracy is acceptable?
Yes, ma'am.
Let's think of that when we do data analysis now, real life data. Then we will see that easily we will make mistakes of 100, a few hundred rupees, inaccuracies, yes. Let's live with it in order to get a little bit of mathematical traction, which normal distribution is a very beautiful distribution. It's a symmetric distribution. It has lots of good properties. uh, and which others don't have. I mean, the others are also in the same family of exponential distributions, but this is the most elegant distribution that is there. So we will give up a little bit of accuracy in order to gain a lot of mathematical traction.
Yes, ma'am. Thank you, ma'am.
Yeah. Good
Hello, ma'am.
question, but yeah,
Ma'am, can you go back to monotonicity?
yes, yes, yes.
Ma'am, I don't understand how this is justified. Why should the risk of P be greater than Q just because its returns are always lesser?
Sorry, 1 minute. These touchpads are so touch sensitive. Okay. Okay, this was your question, right? All right, let's look at it. I don't know what I did. So let's look at it. What did we say? We said that um, monotonicity says, let's not even think of in terms of a distribution because it will confuse. Monotonicity says if this is minus 20 for P, Q would be better, maybe minus 19. P is minus 5. Q would be better. So Q would be minus 4.9. So if my this is my say 95% cutoff. So you see P's value cutoff value is worse, isn't it, than Q's. So my value at risk. Do you agree or you don't?
Yes,
Yes,
ma'am.
ma'am.
So value at risk may be 5 crores, whereas Q's value at risk will be 4.9 crores. Even if you take expected shortfalls, conditional value at risk, it also has another name. Be- because these Q values are always better than the P values. So even the average of these guys will be higher than the average of these guys, right? So when I look at, because P is bad, worse than Q all the time. So that means P is riskier. Think of it, forget maths, forget numbers, forget anything. So P is worse than Q all the time. Doesn't that make P riskier than Q?
Ma'am, what if P and Q both guarantee positive returns all the time?
Mhm.
So wouldn't that make both of them risk free?
Ha! Had such assets which could guarantee positive values all the time? Yes, but we don't have. We are looking at value at risk because we have losses. We are looking at risk.
Okay, ma'am. Got it.
Yeah, and sigma sometimes do not work here because P sigma of Q may be higher, whereas sigma of P may be less. So if you measure risk with sigma, you may end up saying that P is less risky than Q. The only condition in monotonicity is that P has to be worse than Q under all possible circumstances. But sigma of P may still be less, but P is riskier. Think about it this way. P is worse than Q under all possible circumstances. So any measure of risk that you take should reflect that P is riskier. If you take standard deviation, the values of P might be having smaller risk. And so standard deviation may show that P is less risky than Q. But P, remember, in this example, is always worse than Q. So inherently P is riskier. We will not invest in an asset which is always doing worse than Q. So risk measure that we consider should be um, should be able to reflect that worseness. Where CVAR do help you do that, but sigma doesn't. Can you see this? I mean, I don't have a full setup now. I cannot go to Excel because Tab doesn't have Excel. I don't know how to do this. But anyway, so trying to. Could you get the idea? I'm not sure whether you could
Yes,
get
ma'am.
the idea.
Yes.
Yeah.
Ma'am, I have
So
a doubt.
now we are agnostic. Yes, just 1 minute. We are agnostic. We are comparing risk measures. Huh? Yeah. Please, can you please identify yourselves? I'll
Yes,
try
ma'am.
to
Deep
read.
here.
Very deep.
Yes, ma'am. Ma'am, I had a doubt that in translational invariant, how does, cash reduce the risk? Is that what I'm trying to understand?
Yeah. So think about it again here. If you have invested, suppose you have a portfolio, it has you have invested 100 rupees entirely on P, and P can have a loss of minus 20. So you have made a loss of minus 20 completely. But
Yes,
suppose you have added some cash to it. Either ideally you should have 80 rupees invested in P and cash 20 rupees. On this 80 rupees, if you make a loss of minus 20 rupees also, the net loss because of this cash becomes zero, because you can then use up this cash to replenish the loss that you have had in P. You can buy maybe some more of P or whatever, and take that I mean, replenish that loss of P.
got it, ma'am.
Is it?
Ma'am, but the amount
So,
invested is but
yes.
got it, ma'am.
Yeah. So it kind of the cash kind of helps you to whatever loss has happened to you, you can just recover it by buying more of P or whatever. This is a loss, remember. So kind of share prices have fallen, but you can buy more of P so that your portfolio which has become 60 can again be made 80, because now with this cash you can buy more stocks and bring it back to 80. So this portfolio can remain at 80. Yeah, so the risk kind of reduces when you keep cash with you.
Got it, ma'am.
Yeah. Any other question? Okay. So if there's no question, maybe I will. Yeah. So
Ma'am, could you share today's notes on Teams if possible?
yeah, I'll have to see. um, I'll have to see how to save this. And although I really think this note was very badly written, but if you still want, I'll put it up on notes. But try not to follow them because they were not very well written. And anyway, I'll put it up.
Okay.
But I strongly urge you to take your own notes, please. I mean, just waiting for me to put up the notes is a bad idea. I say many things which I haven't written down. You must take your own notes. And going back to video would be, I think, very, very difficult. No? This is the third year you are already into online classes. Do you actually go back and watch the videos again?
Yes, ma'am. Sometimes.
You do? Okay. And I don't think we would have the time to go through again.